You ever stop and think about what's really happening in that split second when you click a link? It feels instantaneous, right? Like magic. But it's actually one of the most incredible high-speed journeys you can imagine. So let's pull back the curtain and demystify the magic behind the internet. So there it is, the click. In a literal millisecond, your computer kicks off a process to send a request, maybe thousands of miles across the globe, find its specific server, and get a full-blown web page delivered right back to your screen. This whole explainer, well, it's the story of that single click's amazing journey. Now, for this to work, for billions of devices, iPhones, Androids, laptops, servers, you name it, all made by different companies, to understand each other, they absolutely need a shared rulebook, a common language. And that's exactly where networking models come in. They're the framework that lets a server in California talk to a phone in Japan without a hitch. The granddaddy of these rulebooks is the OSI model. I want you to think of it as the universal blueprint for how any network communication should work. It was published way back in 1984, and its whole goal was to make sure that hardware from one company could play nicely with software from another. Total game changer. But here's the thing you gotta remember, and Professor Messer says it perfectly. It's a model. It's a guideline. While the internet doesn't strictly use the OSI protocols, its seven-layer structure became the essential language, the common ground we all use to describe, build, and fix networks today. So what we have is the blueprint, the seven-layer OSI model. And then we have reality, the TCP/IP model, which is what the modern internet actually runs on. You can see it's a bit more streamlined, just four layers that kind of squish some of the OSI functions together. For our journey today, though, we're going to stick with the seven-layer OSI model, just because it gives us a much clearer step-by-step picture of everything that's going on. So how does this actually work? Well, when you send data, it travels down these layers, kind of like a package on an assembly line. At each step, a new layer adds its own wrapper, its own instructions, getting it ready for the big trip across the wire. Our journey starts right at the top, where you are, layer 7, the application layer. This is the software you're actually touching and seeing. We're talking about your web browser, your email app, you get the idea. When you type in a web address, you're creating the raw data right here that needs to be sent. That data then gets handed off to layer 6, the presentation layer. This thing is like a universal translator and a security guard all rolled into one. It makes sure the data from your app is formatted in a way that any other computer can understand. And this is huge. It's also where encryption happens. SSL/TLS wraps your data in a secure package so no one can snoop on it. Next up is layer 5, the session layer. You can think of this as the conversation manager. It's like a digital switchboard operator that opens up a direct line, a session, with the server on the other end. It keeps that conversation going for as long as you need it, and then hangs up properly when you're done. Okay, but before we just start blasting our data out into the world, your computer and the server need to do something, well, kind of polite. They need to formally introduce themselves and agree on the rules of the conversation. This is absolutely critical for a reliable connection. So how do they do this? How do they make absolutely sure that no data gets lost or shows up in the wrong order? Well, the answer is in layer 4, the transport layer, and a super important protocol called TCP, which stands for Transmission Control Protocol. It all happens with something called the TCP three-way handshake. It's literally a digital conversation. First, your computer sends a little SYN packet, which is basically it saying, "Hello, are you there? I'd like to talk." The server gets that and replies with a SYN ACK, which says, "Yep, I'm here, and I can hear you loud and clear." Finally, your computer sends back one last ACK packet that just says, "Awesome, connection established. Let's do this." And now they're both ready to go. The connection is live. Our little data packet is all wrapped up and ready. But now it needs an address. It needs to know exactly where it's going in the massive, sprawling network of the internet. And that is the job of layer 3, the network layer. This is the internet's global postal service. This layer is what slaps the source and destination IP addresses onto our data packet. It's basically putting a mailing address on the envelope so that every router along the way knows exactly how to forward it. Now, to get our data to the right place, we actually need two different kinds of addresses. At layer 3, the IP address works like a zip code. It gets the packet to the right city, the right neighborhood. But once it's in that neighborhood, you need the layer 2 MAC address. That's like the specific street address to deliver it to the exact house, the exact device. Which brings us down to layer 2, the data link layer. This is your local mail carrier. This layer takes that whole IP packet and puts it into one final wrapper called a frame. And that frame has the specific MAC address for the very next stop on the journey, making sure it gets from your router to the next one, and so on. Finally, we hit the bottom. Layer 1, the physical layer. Everything we've just done, all that data, all the headers, the addresses, it all gets converted into a raw signal. We're talking about electrical pulses shooting down a copper cable, flashes of light in a fiber optic line, or radio waves for your Wi-Fi. This is where the ones and zeros physically hit the road. And just like that, our data is on its way. The server gets the signal and then does this entire process in reverse, unwrapping it layer by layer until it gets to your original request. It's this layered approach that is the invisible and incredibly powerful foundation of our entire digital world. So why go through all this trouble? Well, because this model is pretty much genius. It means a company making Wi-Fi cards can innovate like crazy without having to worry about how Google Chrome works. It makes troubleshooting way simpler. When your internet is out, a tech can ask, is it a layer 1 problem? Which is just a fancy way of saying, hey, is the cable unplugged? It's what keeps the internet resilient, competitive, and constantly evolving. So the next time you click a link, just remember this incredible layered journey that happens faster than you can blink. This fundamental architecture, designed decades ago, is somehow scaled to connect the entire planet. Which really leaves you with one big question, right? What does the next evolution of this invisible foundation even look like?